Okay, so it's a great pleasure for our second half to be able to introduce Mike Koss. Mike is a MIT alumnus, a Microsoft alumnus. Started at some point buying computing gear off eBay. I don't know when. I remember getting a call from him a couple of years ago because he had bought an IBM 029 card punch, and they had put this 400-pound thing on a pallet, like, in front of his garage. And actually, he's enough younger than me that I believe you never punched cards.
I did one summer when I was in high school.
One summer, okay. And so I remember heading over to their house and trying to move this gigantic thing off its pallet. And the scary thing was how fast. And most of you are a lot younger than me and don't remember IBM drum cards and things like this. This is the way you made these monster key punches skip and duplicate and stuff like that. And somewhere from 30 years before, I was able to dredge up all this garbage about how you punch these drum cards in order to make the key punch do these crazy things. It's amazing what stuff you have in your brain that keeps you from incorporating new stuff. Anyway, the great news is Mike has purchased a lot of World War II encryption equipment and has been kind enough to come over tonight and talk to us about crypto during World War II and these cipher machines and the breaking of the ciphers. We're going to end at 20 after 9 because Mike and his wife have a plane to catch. So we're leaving even if we're not done. So it's important to stick to that time schedule. And Mike, thanks so much for being here tonight.
Okay, great. Can you hear me okay? All right, so my talk today is primarily about the Enigma machine, but I have brought some other coding machines with me as well. And my talk is not going to be so much technical, but I really found it fascinating. I'd read a lot about the Enigma machine, and it seems so daunting and kind of complex. And my goal tonight is to really say it's basically a very simple operating machine, and everyone here will know exactly how it operates and be able to simulate it with a piece of paper. So that's one of my goals, and we'll also talk about some other machines after that. So the history of the Enigma machine is it started out as for business communication. The German Arthur Scherbius in 1918 actually developed the basic device for encoding business communications. And the German Navy picked it up in 26, and they then analyzed it and developed it some more, and they created a modified military version, and I'll explain what it is that they did to modify it. And then later on in the war, they actually added some additional elements to make the system much more difficult to break, and which had major implications for the course of World War II. So the Enigma machine is what's called a rotor machine. It has these 3 rotors inside the machine, and it uses an electrical current that goes through those rotors. But it's not really an electronic device. It's primarily a mechanical device. And electricity is just a convenient way of hooking up a key press to a light bulb. And it basically just lights up a light bulb every time you press a key. So this is a very nice schematic diagram of how an Enigma machine works. You'll see you have a keyboard and 26 keys. It's not QWERTY. The Germans use a Kurzzu keyboard, or at least they did back then. I'm not sure today what they do. And it has 26 lights. And the keys, when you depress a key, it closes a switch, which then, you have a battery in there, and then there are wires, the 26 wires come out of the keyboard, and they start to go through the rotors. And each rotor is basically a permutation of the alphabet. So on the right-hand side of the rotor, there is actually, let me go ahead and start to take out a physical rotor here for you to look at as I'm talking. Where the camera down here. There we go. So here are the rotors themselves, and there's 3 on a spindle. And you can see on one side of the rotors we have these pins, and they're on a little spring-loaded pin. There are 26 pins going around here, and on the other side there are 26 contacts. So when this machine is when this rotor is placed into the machine, the keys that you press here make a connection to one of 26 contacts on the right-hand side, and then that will connect to one of these pins here. And then inside each of these rotors are 26 wires that are kind of randomly connecting these pins to these plates on the other side. And so each of the 3 rotors is like that, and so those connections make their way through all 3 rotors. So you basically get a permutation of the alphabet from each rotor. You permutate once through here, and then through here. And then finally, there's something on the machine called a reflecting rotor, which in this machine is not actually a rotor at all. It's basically, I think it's called the Umkehrwalzer in German. It's a stationary rotor. And it basically just reflects 13 of these pins are connected to 13 other pins. And so it does a reflecting operation. And now we're going to go all the way back through all 3 rotors again, permuting the inverse permutation back through all 3 rotors and then out to this connection again. And that's also connected to these lights, and then a light will light up. So, and you can see that in this diagram where if you followed the letter A, what did I do with the stylus?
Oh, yeah.
I got it. You followed the letter A. Well, actually, A's hard. A kind of goes off the top here, and comes back through here, comes around, back through here, and then it goes through the reflecting rotor.
Sweet.
Are you seeing the ink?
But we're going to shift to red.
Oh, okay. Okay. So you press the A key, it'll come out through here. And we just follow the wires through here as best I can. I think I'm doing it properly. And then
Down to the
where
bottom.
does this guy go?
To the bottom.
That looks like it goes backwards, which is like a mistake in the drawing.
No, just to the
All the way
bottom.
down here.
Okay, down here, okay. Great. Back through here, here, boom. And so you press the letter A, and then the C would light up. Now, one of the things to notice is that because of the properties of this reflector here, you're always going to get a reflective property of the system. So if I press the letter A, I'm going to get a C to light up. But if I press the letter C, I'm going to get the A to light up. So it's a symmetrical cipher. It's every letter. It's basically a pairwise substitution of all the letters of the alphabet. And so no matter what these rotors do here, because they all go through this reflector at the end, when you unwind all the permutations, you're always going to end up with a pairwise substitution. So that means that when you take an Enigma machine and set it up to encode a message, then you set it back to the original state again, and to decode the message, you don't have to do anything to the machine separate. There's no encode mode or decode mode. So that's the basics of how it works. And I'm going to describe a little bit of the protocol or the procedures that were used in actually using the machine, because some of these protocols actually had a lot to do with how they attacked the machine and what kind of weaknesses it had. So this is a picture of the rotors themselves, and first, if you actually go sit down and want to read about how an Enigma works, I was very confused when I first read about how to operate an Enigma, because there were a lot of things they talked about that I didn't understand. It didn't seem to make a lot of sense. I knew about these rotors, but they had this thing called a ring setting, and like, what is a ring setting? I didn't really understand that. I'll go down here to show that. One of the key features of an Enigma rotor is this little notch. And this notch is basically what controls the odometer-like feature of the Enigma. So one of the reasons the Enigma is more secure than just a simple, cipher is that the code changes for every letter. So every time you press a key, not only did it go through that whole step of encoding that letter and lighting a light, but the rotors also move for every letter. So now you have a different permutation for every letter of your message. And to control that motion, the right-hand rotor always moves, so it's always just kind of ticking over. But then this notch actually controls when the rotor to its left will move. So you can't really see on the television camera inside the machine itself, but there are these 3 pawls. Oh, you can kind of see them moving there.
You can see better than that.
there's these 3 pawls that are in there, and they're kind of like on a spring. You can see I can push them back with my finger. So if they don't line up with one of these notches, they just kind of slide along the wheel, and they don't do anything at all. But if they line up with a notch, it'll be like a ratchet, and it'll click that wheel over 1. So the position of this notch tells you when the next rotor is going to move over. And so what is a ring setting? It turns out that this notch, the position of this notch is not static with respect to the wiring pattern here. You can move the notch around in a circle to any one of 26 positions.
Sorry, Mike, is the wiring pattern fixed, or can you reprogram?
The wiring is fixed for each wheel. Like this wheel is number 3. Wheel number 3 has a very specific wiring done in the factory, and nobody ever opens it to change it unless it needs to be repaired.
Arbitrary?
It's not arbitrary. I'm sorry. And I don't know how the Germans designed the wiring pattern. As far as I know, it was randomly selected at some point, but then it's fixed. So the ring setting basically lets you decide how the rotors are going to move. At what position will they actually kick over and rotate the wheel to its left? So that matters. If you know the starting position of the wheels, you could get confused if you don't know where the notch is, because all of a sudden the code will change, and that means the center rotor's changed on you, and you just didn't know where the notch was in the right place. So that's how that works. So that's how we start out with it. The Germans would publish a code book that would have a 1 month worth of keys. And so the key setting for the machine starts out with the ring setting. So every day, and they mostly did this on a 24-hour cycle, they would have a book, and you'd look up, okay, the ring settings, I'd have to set that notch position to one of 26 positions for each wheel. For my case, we're going to just leave them all on AAA, and because it's kind of a complexity it doesn't really change the fundamental coding mechanism. It just changes when that wheel actually rotates. And if you've looked at that paper Enigma that I created, it doesn't have any ring setting, so it doesn't simulate the ring setting. It just kind of assumes it's at AAA.
Question from San Diego?
Yeah.
You had basically mentioned that those wheels had numbers, like the 3 on that one. Now, did each Enigma machine come with its own set? Or, if one of those broke, can you order another number 3 to replace the number 3 that broke in yours?
Yeah, so the question was, does each machine come with its own set of wheels? Is that right? Or?
That's right. Or were those wheels interchangeable? If a wheel broke, you just ordered a wheel through the serial number. Or was each Enigma equipped with its own set of wheels? And once it broke, you had to order a whole new set.
Yeah, well, each Enigma, the way the German communication system worked is there was a lot of, in order to each kind of area of battle they would share, anyone who would ever have a need to communicate with everyone else, they all need to share the same keys. So these were very standardized, and I believe that absolutely every Enigma of the same type, they all had the same set of wheels, and in fact, every Enigma machine you look at, they're very obviously secretive about controlling the distribution of anything that's as secret as these wheels. These were things that that people were told to kill themselves rather than give up these wheels, and so there was a lot of secrecy around protecting those. Each one has a serial number, which is the same as on the box. On the back of the box here, I can see the serial number for the Enigma itself, and the same serial number is printed on each of these wheels. So they're matched set, but they are identical in manufacture to every other Enigma, but they wanted to control and make sure that they didn't lose them. They knew where it came from. And later on in the war, they did add additional rotors. So there's a box of, I only have 3 of the original rotors, but there were, I believe, a box of five or 6 available rotors to choose from, and that was one of the things they did to increase the complexity of breaking the Enigma.
Question for Microsoft.
Yeah.
What was the state of the art in manual ciphers before these Enigma machines came out? Was this all done just by paper with a similar sort of cipher, or was it something else?
Well, that's a good question. I actually do have one of the earlier machines here. This is called a U.S. Army M94. This is an example of a kind of a device that was used prior to the purely mechanical devices. This machine was actually invented by the French prior to in the 18th century sometime, made out of wood, and they're basically this is 25 rings with a random permutation of the alphabet on each of these rings. So there's 25 wheels here with the randomly permuted alphabet on them. And the way that this device would work is that you can rotate these wheels. You unscrew this and loosen it up. You can rotate all these wheels so that you can line up a message along in a row here. And the key here is what order the wheels are on this spindle. So that's the secret key that you would have to know. So once you have that key, you put the wheels on in the right order. You line up your message here. And then to encode something, I think this is really clever. You just take any of the other 25 rows on this device, just choose it at randomly, and then that's your encoded message. You're going to have that line of characters. So you write that down on a piece of paper, you send it by courier. This was used during the Civil War as well, pretty extensively. Not this physical one, the aluminum one only came later on. But then when you receive the code, you would have to line up the encoded message somewhere here, and then it's your job as a human to recognize which of the other 25 lines actually had something in English to say to you. And hopefully you wouldn't have the very bad luck of having one line say, attack at dawn, and the other line say, retreat immediately. That would be pretty improbable. So this kind of a mechanical device was one example, but I think most of the prior state-of-the-art was paper and pencil systems. There's some famous, just simple Caesar codes. There's and actually.
How much does a device like that go for today? Just out of curiosity.
Which one?
Not the paper one, the previous one. The M94, I believe.
M94. I think I paid $5,000 for this. This was the very first. So I'll tell you a story about that. This is a big segue, but this is fine. So when I was 9 years old, I had this book, which was Martin Gardner's Codes, Ciphers, and Secret Writing, which really inspired me a lot. I loved the idea of writing secret messages. And in this book, he describes all kinds of interesting ciphers. A lot of them, answer your question about the early cipher systems that people used when they were developing, back from the Roman times, where they would wrap papyrus strips around a rod. I think I call that a skytail system. And you can't see this on the camera very well, but here's a picture of the M94, which was in that book. And when I read this, I saw this as a 9-year-old thinking, oh, that would be so cool to have one of those things. And whenever then through the 60s, 70s, 80s, whenever I would meet someone who was involved in antiques or some sort of, obscure dealings like that, I would ask them, hey, have you ever seen one of these things? And of course nobody had, and so I had no way of knowing how to find one. And unfortunately for me, the internet was invented, and eBay was invented, and then I started looking on eBay for anyone selling anything like this, and this was the first one to be sold on eBay. And I think there were probably a lot of people like me who were looking for this thing. It got bid up. I remember the weekend where the auction closed, and I was actually at my aunt's house using her dial-up connection to outbid all the other people who were trying to snatch this thing up. So this sold for $5,000, but I think the very next one, someone else had one who sold one 2 weeks later that sold for only $3,000. So So I paid a little bit of a premium to get the first one. Okay. So on the slide here is an exploded view of what the inside of a rotor looks like. So you can see very finely crafted German engineering and skill in creating this thing. And you can see the wires kind of over on the left side, some of the wiring, internal wiring for these. Okay, so what's the next part of the key for an Enigma machine? And that's the plug board setting. This is also another feature that I do not have on the paper Enigma. This was the innovation that the Germans added basically after the business kind of commercial machine did not have this. And the Germans recognized that there are only something like 17,000 positions of these rotors, 26 to the third power positions of the rotors, times 6, 3 factorial for the ordering of the rotors. You can put them on in any order. And so they wanted a system that had many, many more possible key sets than this, millions and millions of keys. So what they did is they created this plug board on the front of the machine, and that basically just does an additional pairwise substitution of letters. So if you plug, as in this picture, the C is plugged into the M. The C and M plug are plugged into each other, and so that means where before, anytime the effect of pressing the C key now is the same as the effect of pressing the M key instead, and vice versa. So it's an additional pairwise substitution on top of the whole system. So again, because it's a static kind of system, as an afterthought, kind of above and beyond the rotary system, I didn't include it in the paper Enigma. You could do that by hand later if you actually wanted to include the effect of a plug board.
So did they usually plug in wires for every single letter?
Yeah, the daily key usually had between 6 and 10 different plugs that you would plug in here. So there's a lot. So it's 26 choose 6 or 26 choose 10 possible combinations. It's millions of possible combinations. Okay, now a nod to my alma mater here. I'm going to use MIT for the initial rotor setting. So the last component of the key is the initial position of the rotor. So it's also it's the ordering. So you have the ordering of the rotors on the spindle, the ring settings, then the plug board settings, and then finally the starting position for the rotors themselves. And that's the same also. You get this out of the code book, and it's the same every day. So let me set up my machine now to the MIT setting, or my machine happens to have numbers instead of letters in the little windows on the front of the machine. So it's 13,920. So let's see. I have rotors 1, 2, and 3 here in order.
Can you say that rotor 1 is on the left and that has the setting M?
That's correct. So what did I say? 13,920. So 13, 9, and 20. So now the Enigma machine is ready for use. So ready to begin. Okay. Now there's a fundamental problem if every message sent today, you have thousands of military messages being sent every day. If they just use the code book, then every message would be sent with the exact same key settings. And even though it's changing for each and every letter, the nth letter of the message is being sent with the exact same simple alphabetic substitution cipher. Even though it's arrived at this complicated mechanism of permutations and rotors and things like that. And so if you think about it in the German, if all these messages are in German, if I do a frequency analysis of the the 20th letter of every message sent that day, I will tend to get a very unique distribution of letters. That reflect the distribution of the letters in the German language. And if every message actually were encoded that way, I could do kind of this parallel analysis where I take all 1,000 messages I've intercepted that day, look at the 20th column, do a frequency distribution and guess letters for that, the 20th position. And then in the 21st position, I could go do the same thing again. And so by that method, you could actually go and crack that if you have enough traffic. So Germans were not stupid. They were quite aware of this phenomenon, and they took care of it by allowing the operator to choose a totally unique key for his message. So the only thing that the codebook key was used for is just to send what's called an indicator, or a sometimes called initialization vector. If you read other kind of cryptography, kind of modern cryptography systems, you have a way of initializing your system, and that you want to choose to be like a random number. And so I'll choose MCK, my initials, to be, which is probably a pretty poor choice if you know the message is coming from me. And that's going to be what I'm going to use for the rest of my message. So what the Germans decided to do is that they were very, the Germans are very detail-oriented people. They don't want to make mistakes. They want to make sure that everything's going to work very smoothly. So they decided to send that message indicator twice. And so you could catch an error. If you miss the message indicator, you will have no hope of decoding the rest of the message. So they said, well, instead of just putting it out there once, and all these things, remember, are being sent with Morse code eventually. So all the messages are being coded manually on the Enigma machine, written down on paper, and then sent to a code operator who would tap it out in Morse code, and another guy on the other end listening to Morse code with a lot of static and so on, writing down the message, and then finally taking it to his Enigma, where they would type it out and try to decode the message. So, if they just miss one letter, they wouldn't be able to read the message at all. So they said, let's give him 2 shots to get the message. And so, in my case, the beginning of my message would then begin MCK, MCK, and then that would start out every German message that was sent using Enigma would have these 6 letters for the message indicator. But instead of, obviously they don't want to send that in the clear, so they encoded them. So they used the machine to encode them. So in my case, if I type MCK, and here we'll see if our machine works here, M, and so if I see I pressed the M down and the N light lit up, and then C, now the W light lights up, and then I press the K, and the D light lights up. Now I'm going to repeat it again, MCK again. I get an S, an H, and an E. Okay, so now
because one or more of the rotors have...
that right-hand rotor is changing every time. So if you look at the machine, if I sit here and press one letter, the letter P, I get an H now I get a J, and now I get an S, and now I get a V, and now I get a B, and it's changing every letter of the cipher. So I've just sent my message indicator, and so what will actually be sent out in Morse code is NWD-SHE, and the operator on the other end will know how to decode that and then figure out that I said MCK, MCK. So now for the rest of my message, I set up the machine with the MCK setting. So that's 13.3.11 in my case. Okay. What, did I go backwards? Okay, so then I type the body of my message. So in this case, I have the message Enigma revealed, and I won't go through the whole thing, but the E goes to a Q, the N goes to an M, the I goes to a J, etc. So if you go through the whole message, Enigma revealed gets to Kimjido Jiffer.
San Diego.
Pardon me?
Question from San Diego.
Go ahead.
So when the operators are supposed to choose these indicators randomly,
Yeah.
when they're sending the message, do you have any sense for how good the operators were at choosing these, or whether sometimes the same indicator would be repeated and leak any information that way?
Well, what do you think? Human nature, yes. The
human-
average code operator was probably a 19-year-old, and they were often like the initials, their girlfriend's initials, HIT and LER. Those were very popular message keys. BER and LIN. Or QWE. Consecutive letters on the keyboard itself. They're racking their brain. Oh, what do I use this message? And they often chose pretty poor message keys.
So did this help at all, or would it have been just as bad to just use the code?
Well, they always used the code book to encode their message key, but then the rest of the message was something just the operator decided on their own.
So like if you had the code book and you listened at the beginning, did you just get this key anyway?
Yes. So you don't need that. So now if you want to just guess what those codes are, if you had an Enigma machine and you just wanted to guess these common mistaken, really poorly chosen indicators, you don't need the code book at all because it's irrelevant at that point. So that was really bad, and it did happen quite a bit. So that was one of the breaks that they used in solving it. So again, like I said, the setup for decoding is just the same as encoding. You start out, you set it up to the daily key. You type in that NWDSHE. You confirm that it decodes to a valid-looking message key, two 3-letter groups that are identical, and you set it up like that. And then because it's a symmetric machine, then you just set it up exactly the same way, and then type in the code, and you get the original message.
Question.
So,
So
is that a question?
Yeah, question here. So initially they had the code books, and then when did they go to where the operators were basically allowed to set their own initialization key?
Always. I think from the beginning they always did that, I believe.
Okay.
Yeah, do you have a...
Yeah, a question. So I think there's no space key, right?
There's no space key.
What's that for a reason?
I don't know, just economy. Telegrams typically didn't have spaces necessarily either, and you just get blocks of letters.
No space in Morse code?
I'm sure there is a space in Morse code. I don't happen to know it. It's not normally.
You just leave space. Stop.
Yeah, you just leave space in the air. Yeah, and typically you'd send these messages in 5-letter groups on the air. So you just chunk it up into 5-letter groups and send it that way.
Because otherwise you'd be able to guess like just by length of words.
Yeah. Now, a really interesting aspect of the Enigma machine, because it is, I can talk a little bit about some of the security problems with it, is that because it has this symmetric encoding ability, a letter can never encode to itself. So if I type an A, I will never get the A light to light up, no matter what the machine setting is. So now take, for example, suppose you have a guess about what a message might be, or it might mention something, like, say, and a pretty long phrase, like Herr Kommandant Frankenschnitzel, A lot of message traffic would begin with a very formalized German, dear Herr Kommandant, Frankenschnitzel, I'm sorry to report that we lost a refrigerator in the field or something. I don't know, whatever. But all those messages would begin with like these very formalized long phrases. That's long enough that if you just took letters at random, so say you had, I don't know how many letters that is, but say you have 25 letters there. It's unlikely that if you choose 25 letters at random, none of them are none of them are going to you'll get at least one letter to be matching up. Just at random, you have 25 chances for one of them to line up. So what some of the code breakers would do is they would guess phrases, and then they would take that phrase and just pass it along the Enigma ciphertext. And if there's ever a case where absolutely none of the letters are matching the original message letter, then that's a possible location for that word to actually be the word you're trying to encode there. And so that would then give them a clue about what the machine settings could possibly be. So that's a kind of it's a subtle vulnerability, but it was used to help break into codes.
Question about that?
San Diego.
Yeah.
How much of the actual protocol for the use of the machines did the Allies know when they were working on breaking the codes?
Well, okay, the story of breaking the codes is actually goes back to the Poles. Back before the outbreak of war, before the Poland was invaded, Poland was, of course, very nervous about the increase in German military force, and they knew about the Enigma machine. You know, it predated it was a well-known device used in business communications, and they had a good idea that the military was using this kind of a machine. And they actually did do a lot of the early work, and they understood quite well how it was being used in practice. And I think one of the really interesting stories is that in Warsaw they recruited the most brilliant mathematicians that they had in that particular class that year, and said, "How would you just like to work on breaking codes?" And they actually came up with very innovative ways of attacking this machine. By making, it sounds pretty tedious now with the lack of having a computer, but they actually made catalogs of the characteristics of how each setting of the machine would permute the alphabet. It's a little complicated. I get kind of lost about it myself, but basically, if you think of like any one setting of the rotors, and you have this message indicator capability where you know that the first 6 letters are always repeated, or the first 3 letters are repeated again. You can make a correlation between the first letter and the 4th letter of the message, because you know both of those were originally typed with the same letter. But in one case, an A might be a Q, and the next time the A will be a Z. So now Q and Z are somehow related by the fact that they're 3 steps away on this particular rotor setting. And you can follow that. So if you had a machine, you could sit there and make a catalog. You can say, okay, for rotor position 111, I'm going to type A, and I see what letter I get. And then I'm going to take that letter, and I'm going to reset the machine back to that position again, and I'm going to type that letter. And you end up being able to catalog the permutation of the alphabet that relates the first letter to the 4th letter. And you will have a certain number of cycles. Like you'll get some letters will be the same. In fact, sometimes just by chance the 2 permutations end up with the same letter. Or sometimes, when the first letter's an A, the next one's a Q, and when the first one's a Q, the next one will be an A. So you get a little 2 cycle in the permutation. And I don't know if you're familiar with cycle notation. If you write down any permutation, you can always write it as a series of cycles that are kind of multiplied together as a permutation. So any permutation of the alphabet has a kind of a signature. Like it might have 3 single cycles, 2 pairs, and then a 5 cycle, etc. So that signature is a characteristic of that particular permutation, and it's related to which rotors are used in which position. And so what the Poles would do is they would get enough messages during the day that just operators at random are choosing letters in their own, and they're basically giving them fodder to say, oh, you know what? Whenever we saw a message where the first letter was M, the 4th letter is Q, and they would kind of add that little bit of evidence in until they had enough messages they could build up the entire permutation of how first and 4th letter were related. And then so they did all this work up front to make 17,000 3x5 cards describing every permutation, and they sorted them topologically by their size of their cycles so that they can then go back and look it up. So when they got a bunch of messages during the day, they say, oh, the characteristic of today's rotor settings is 5 single cycles, 2 double cycles, and a 5 cycle. They go to their catalog, and there's only 4 settings of the rotors that have that characteristic. So then they would just try those 4. So it was able to kind of narrow down this much larger space down into just a few things that they could then do trial and error. So that was really a brilliant observation by these early mathematicians, and I'll have a little more on the slide on that later.
Question?
Yeah.
So in regard to a letter never being ciphered back to itself, were the Germans aware of the vulnerability this introduced, and why would they have designed it that way?
I think there was a kind of a sense of hubris involved in it. I think that they felt that they really had done a really great job at designing something that was really secure and didn't bother them, that aspect. So, I think had they maybe had a stronger, I don't know, I have not read very much about the German cryptanalytic or cryptanalysis section. The British actually created a really large organization to do breaking codes, and so it's always a good idea if you're generating codes yourself to have an equally or better team of people that are trying to break your own codes so that they can come up with all these things. And I don't know how much the Germans did do that, but they felt really confident in their machine, I don't believe they ever really suspected that their machine could be broken. It just seemed too impossible. It's so many combinations to get through. They didn't realize there were these little shortcuts.
Once they learned about computers, did they think that they were in trouble?
Well, the invention of the computer is kind of contemporaneous with the end of the war, and actually kept as a military secret as well. So the first stored program computers in Britain was the Colossus, and it was a secret up until the 70s, I believe. The British actually didn't reveal that they even had done such a thing. So.
Yeah, but wasn't Zeus doing things?
Yeah, I'm not as familiar with that. What was the year that Zeus came out with his computer?
36.
What?
36.
36. Yeah, so that would be a way to attack these machines, obviously, computers. So I don't know the answer to that question, how much they thought about that.
Turing, by the way, again, Turing's involvement in Colossus, or maybe in a different machine, I forget, only became known with this declassification in the 70s. So Turing was viewed as a pure sort of computational mathematician until the 70s when it was discovered that he was building hardware.
So as for a letter mapping to itself,
yeah,
because you've got a current going through there, you'd have to have 52 letters on your rotors. If you had a letter come back to itself, it would close the circuit, right? It would short.
Yeah.
So it would have been a huge cost to map letters back to themselves.
Well, if you don't use a reflector, I think if they got rid of the reflector, you could put lights on the far end of the permutation and then forget the reflecting. But then you'd have to have a different set of rotors or you'd have to put them in the opposite order backwards and set up the machine or have a switch to encode mode versus decode mode, and then you could get rid of that problem as well. So, but they like the simplicity of having, one setup. So I don't know if you can raise your hands if you have cut out your paper Enigma and have it ready to go. So Microsoft guys, those are doing good. UCSD, pretty good. Berkeley, I don't see any hands. There we go. Okay. I'm going to walk you through, and here in the room I have some more at the back table if anybody wants some more, and there's some scissors here. We're going to walk through kind of doing this thing for yourself on paper, and I think you understand the concept, but it's nothing like practical experience to really teach you whether you understand it or not. Huh? Oh yeah, I have a half an hour to go. Okay, so I think we're doing okay.
We have all night.
Yeah. Okay, so the paper Enigma is basically my attempt to take the inner workings of an Enigma machine and to realize them in a form that you can visually, simulate it or manually simulate it. So if you take the strips of a paper Enigma and the strips represent the rotors, and instead of wires, I have two columns of letters where, when the right-hand and left-hand column of each quote-unquote rotor are equivalent, that means that there's a connection between those two things. On the right-hand side is what I'll call the input-output, so that's the keyboard and light combination. And so you start out, with the settings of the machine. And the way you set the machine is just to have the first three, the MCK setting of the machine is how you'll first position the rotors so that the M on the lines up in the top row of the paper Enigma of the first rotor. So you get MCK lined up across the top, but before you start, remember when you press that key down, the very first thing the Enigma machine does is it kicks that pawl over, and so the right-hand rotor always moves up one first. So in actuality, the coding will begin with the rotor setting MCL.
Yeah.
Everyone got it? Okay. Okay, so then we're going to start on the right-hand side. So you would type the letter E over here. This is great having a little drawing on the slide. This is great. You'll go across to you'll find that just by coincidence there happens to be an E on the rotor itself on the right-hand side, and then you look to the left-hand side of that rotor and you'll see it's way down here where the other E is, and that's kind of where the wire goes through, and then the signal's going to exit out that straight across to the next rotor. And there you should see a Y on the right-hand side, and then find the Y, the corresponding Y on the left-hand side. Is that working for everybody? Yeah. And then straight across you get a V, and then on the reflecting rotor you get a J. So go look for it. There's only one other J on here, and you'll see it's there. And then we come back through, and just by coincidence it happens to be a J on the rotor again, and you find its matching J. And that becomes a P, and you find its matching P, and then you find a D, and it's matching D, and you finally come out at the letter Q, and that's the answer. And that matches exactly what the Enigma machine. So I designed the paper wiring, as so to speak, is identical to the authentic German Enigma machine. So you can compatibly send paper Enigma messages that can be read by an actual German Enigma machine, as long as it has no plugboard settings and the ring settings are all 111.
Can I ask a question? So,
yeah, question.
Isn't the position where these arrows are, relevant to where the notch settings are? You said
that's right. Yeah, you have to. So now, as you encode through multiple letters, you're going to always move that right-hand strip up for each successive letter. But then, when that little arrow, I have a little arrow on the left-hand side of the piece of paper. That's a notch. And when that notch appears on one rotor, that will force the rotor to the left to also move up one notch. Now, there's never a case where a rotor can move twice. The only situations that can happen, actually, are right rotor moves once, right rotor and center rotor move once, or right rotor, center rotor, and left rotor move once. You can never have a case where right rotor moves and left rotor moves. So it's not actually an odometer type mechanism because there's no true carry. There's no true carry system in the way the rotors work. Since it just uses these little notches, you can get the center rotor actually moving twice in a row. It's kind of a stutter step. And that actually was a difficulty for some of the cryptanalysis. When those stutters would happen, it would be surprising to them, and they'd have to kind of account for that and maybe redo some their trial and error guesses. So so this is when I talk about the rollover here. So when the notch arrow reaches the window, you move the one to the left.
So what's the notch on the left rotor for them?
Well, every rotor has a notch, and because you can put it in any position. Yeah. So.
Now, stuttering is a mechanical defect, or it's a property of the...
It's a design property. I don't know if it's a defect necessarily. It was much simpler to make it behave this way. They just wanted to make sure that you'd essentially travel through most of these 17,000 positions of the rotor key space without repeating. They don't want it to repeat too soon. And so with 3 rotors, you'd have to have, you're generally going to have pretty small messages, and they wanted to make sure that essentially you're going to never repeat, any rotor position, and so they just essentially wanted it to approximate, every possible combination of the rotors. And if they missed, a few hundred actual positions that were never reachable, that didn't really matter. So, so that's how you do it. And if there's a message at the bottom of the paper Enigma kind of example section, you can I think it just says Enigma revealed, but it's that you can go through and make sure you understand how it works. And I think when you get to like the 8th letter or something of the message, you'll get one of these notch things to roll over, and you'll have to make sure you kind of understand how that works right. So I wanted to take a little bit of time to talk about breaking an Enigma, and then I'll actually at the end show some other machines as well that were follow-ons to the Enigma machine. So, like I said, they recruited a bunch of grad students from Poznan University, from the mathematics department. There wasn't a computer science department for them to be associated with in 1929, and they did this mechanism where they cataloged the all possible rotor positions for 3 rotors. And they actually built some devices as well, which were mechanical, stepping. I think in order to help them build these catalogs, they built some mechanical machines that actually stepped through simulated Enigma machines and stepped through these different possibilities. There is a story I've heard. I'm not completely sure it's true, but it's an interesting anecdote that the Germans at one point mistakenly sent a Enigma machine in a diplomatic bag or something, or through the post to an ambassador in Warsaw, and the Poles were alerted to the fact that, hey, there's some diplomatic pouch is coming through the mail. They held it at the post office over the weekend, disassembled the machine, got all the wiring settings for the rotors, put it all back together, and then delivered it on Monday morning, and with the excuse that, our postal system is very inefficient. I'm sorry, we delayed your package. And but then they were able to build. They knew then they had the wiring settings for those rotors. So recovering the wiring settings would be extremely difficult if you didn't have that as a hint. So I don't think they ever did that directly. I think they used kind of espionage and actually stole those things. But the Germans added, at some point they added additional rotors. Let's go back.
So this wasn't a 5-rotor machine. It was.
This was a 3
substitutions for the 3 rotors.
This was a
different wirings.
Well, it was I think I'm not exactly sure the chronology, because some of the stories about this don't really set it completely in a timeline. And but there were only 3 rotors in play as far as the Poles had broken them. And but then the Germans added an additional 2 rotors into the set, and so now they had 5 to choose from. And just the manual process of having to do this, it was both overwhelming the Poles, and also the Germans were imminently going to invade Poland, and they realized they were about to lose all ability to read the German messages. So they arranged for a meeting. They tried to give it to the French first. They arranged for a meeting. And the French kind of poo-pooed the whole thing, and
they were too busy retreating.
Didn't take any of the knowledge that they had. But finally, they made contact with the British, and the British happily recognized that this was a very important breakthrough, and they gave them everything they knew about the Enigma. They gave them an actual model that they had built. They gave them, all the knowledge of how they were doing these characteristic settings and things like that. And so now the British would then have to take over the effort of breaking the Enigma on their own against a much harder system now with 5 rotors. So the British started what they euphemistically called the Code and Cipher School at Bletchley Park. And the way they recruited for the school was they took out an ad in the newspaper. The ad didn't say, "Would you like to solve codes for a living?" The ad said, "Would you like to enter a crossword puzzle contest?" And so there were thousands of Britons that happily entered this contest, and if you did very, very well, you were let into the back door. It reminds me kind of Men in Black. They have that little Will Smith taking the test, and the other 4 recruits are not quite cut out for that sort of work, but occasionally they would find someone particularly brilliant, really great mind for solving puzzles, and that's typically the qualifications that most cryptanalysts had, up until this time. The amount of kind of theoretical mathematics being applied or technology really wasn't a recruiting point, or wasn't really understood that was an attribute that people would need. But they've had these very clever people that were great with language and great with puzzles, and that formed the basis of most of the cryptanalytic staff at Bletchley Park. But they did have the fortune to hire mathematicians like Turing, and he did become involved, and he had a lot to do. With, I believe, some of the techniques they used for mechanically decrypting Enigma machines. They had a very clever system where they realized that, similar to the the cycles you could see in these characteristics, messages. A given setting of the rotor would set up other kinds of permutations between one position of the rotors and following positions in the rotors, but without a lot of traffic necessarily being decoded. Figuring out which one of those it was, you could do it through trial and error. And if you had a mechanical system to actually search through all those things, looking for these cycles, you could solve codes. And so they built these things called, with the Poles, actually their machine they called a bomb, and so in the Bletchley Park they also called their machines bombs. Now these were not truly computers per se; they were also electromechanical devices. Purely, I guess you could. They were not really stored program computers. They're very special purpose machines that would purely step through combinations of Enigma rotor wheels, but they were cleverly programmed to recognize a particular type of a cycle. So they would, I think they would use kind of guesses about text that would be in the message. And then using that guess, they would wire up these plug boards that would detect a cycle between like the first letter of the message, the fifth letter of the message, and the third letter of the message, and eventually kind of coming back to the same letter. So they would kind of work on these little puzzles to figure out how to program these bombs to recognize once they saw a cycle like this. And then they had just these, simulated like enigmas that were multiple enigmas at a time, kind of all churning through this. And they had banks of them filled in the whole room. And they used the women, the Navy, I don't know, are they Wrens in Britain? The women would man these bombs, they'd program them, and then they'd just stand there patiently in front of their machine, making sure it was operating properly. And then a bell would go off when it found a potential position that might solve today's code. And they were interviewed later on once they were allowed to talk about it, and they felt like they had kind of won the lottery when their particular machine was the one that rang the bell that day, and they were got really excited about it. The other thing I can just mention for on Turing, the other system that he actually broke and had a lot. I think probably, I don't know the relative ranking of the difficulty of the problem, but there was another system called Fish. The British called it Tunny or Tunny, I think, it's like a tuna fish. They would. It was a teletype system that basically was just an XOR. It was a system that created kind of these random 5-bit sequence of letters, and they'd XOR those letters with the message, and then automatically send that down a teletype wire. So it wasn't a system that was like manual like this. It was a totally automated system. I press a key in Berlin, and then in Vichy, France, the result pops out on the other side on a teleprinter. And so that system was a very high-level system used primarily by direct communications, upper-level command. Hitler himself had used that system for messages to his high-level generals and so on. So that was a really important system for them to solve, and that was one that Turing used, the Colossus machine. So Colossus was not used to solve the Enigma machine itself. It was used to solve this other machine, this Fish machine. And Colossus was purported to be the first stored program digital computer. It had kind of these weird paper tapes that would spin by at very high speed with optical readers, and it was incredibly sophisticated for its day, and it was all done with vacuum tubes. And of course, you probably read about in your history, like using vacuum tubes, they have a very high failure rate compared to semiconductors. And so one of the real big challenges is, could you build like a 10,000 tube machine? What's the mean time between failure? Is it going to be 3 seconds? Is it going to last for a day? How long will the thing run? So that was a big challenge for them as well. I think we talked a little bit about this. The double indicators was revealing some vulnerabilities in the machine, poor choice of message keys, and the fact that a letter never encrypts to itself, which allows you to have this known plain text attack. Here's a better picture on the slide of the M94, which, again, Jefferson actually holds the patent for this machine, but there's strong evidence that he stole the idea from a previous French device, but he decided to patent it in the U.S. Now this is an interesting machine, the M209. I'll go walk over to the table here again. I don't know if is the camera operator here? There we go. Great. So the M209 was a World War II machine as well, so like Vanna White. And this was used by the U.S. Army. And some interesting aspects of this machine is it's totally mechanical. It is not electromechanical, so no battery required, no power source required. The way you operate this one is you dial in, there's a wheel here that has 26 letters on it. You dial in a letter here next to the indicator that you want to encode. Then you rotate this crank, which does a bunch of mechanical stuff inside, which has the effect of spinning this wheel some number of positions away from the original letter. And then you read the result on the inside wheel over here. This one does have an encode versus decode mode. And the way this one, it's also a form of a rotor machine, but it uses rotors in a different way. So this has these rotors, which again are the key settings. It's very complicated to set this machine up, though. There's you really can't see it on the camera, but next on the sides of each wheel, there's a little metal tab that you push in or push to the left or push to the right of that wheel. And then what happens when you turn this thing? See this cage back here? This cage is turning. On the cage, you have little tabs here which will engage the little strips of metal that come out of each wheel as they pass by. So in a sense, this thing it's kind of an adder. Was that a question?
No, it looks like a music box.
Yes, kind of like that. Where instead of playing notes, it's actually ticking this thing forward one notch when it contacts it. So as you turn this cage around, there's 25 different bars here, and so you have some chance that one of these tabs is going to engage one of these wheels at that position and then click this over by one notch. And so ultimately this thing can turn anywhere from between 0 times and 25 times depending on the position of these little tabs and these pins. Another interesting thing about this one, if you'll notice how these wheels turn when I encode something, they all move one space. And at first glance, I was very confused by this. If every wheel is moving in lockstep in synchrony, then you're going to repeat as soon as they all come back around to the beginning again. But that doesn't happen. Does anyone care to venture a guess as to why?
Do they have a different radius?
Different radius, exactly. So each wheel has a different number of letters on it. And so they appear to be moving in synchrony. They're moving all by one letter at a time, but each wheel has, I think they're all relatively primed to each other, so they each have a different number of letters on them. So they, in fact, do go through a non-repeating sequence until you get through the entire key set. Very clever, yeah. So it also has a handy, I don't know if you can see that little weird circular indentation. You might go, what is that for? Mm-hmm. And it's for putting it on your knee. So when you're in battle, you would put it on here, and there's actually a strap. You can connect it here, wrap it around your boot, and you can hook it up on the other side. So then you could be in your foxhole or running through the trench, and be crouching down and decoding your messages on the run. So much more portable machine than an Enigma machine. This one generally took 3 operators, someone to read the message, someone to type the message, and then someone to read the lights and then write it down. So you need like a truck, and the operators here. This one could be a paratrooper could drop in with one of these machines and have it be very portable. What?
Is it more vulnerable than Enigma, or is it less susceptible to crypt analysis?
I believe that this was this is called the class of machine. This is called a Hagelin type machine, and I believe it was never broken by the Germans at all. And I don't know if that reflects necessarily much difference in complexity. I mean, in modern days, these have been broken, but I think it is generally a more secure system overall. So then the Swiss came out with this machine, and they called it the Enigma machine, or New Enigma machine. And this was after the war. And they developed this machine. They added a lot more rotors here. I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 black rotors and a red rotor. And it's very similar in terms of like keyboard, lights. They had the innovation of many different power sources. You could there's even a plug in here that you can plug into a light socket to power it. If you're in your apartment, you unscrew the bulb and you can power your crypto machine. And then if you notice the wheels, I don't know if you can see how the wheels are rotating here, but they are all moving all higgledy-piggledy. It's not odometer style at all. And in this machine, some of the rotors control how the other rotors move, and then other rotors are purely for scrambling letters. So this device was a secret of the Swiss government until fairly recently, maybe 15 years ago, 10 years ago maybe. And then they declassified them, and then they flooded the market with them. So if you want to collect an early kind of machine like an Enigma, this is the poor man's Enigma. You can get this for a few $1,000s instead of $20,000. And these probably show up on eBay quite a bit. The M209 also shows up on eBay quite a bit. They used to be about $1,000. Now I think they've gone up in price recently. This is just an example of kind of the evolution of, I'll kind of come over to here again, of miniaturization. This is called a CD57. So this is your Cold War spy portable crypto machine, and I believe this was actually used that might even be used today in some places. It was illegal in Britain to own one until very recently. It might still be illegal. I'm not sure exactly. And so you can imagine spies in South America or whatever having these things and traveling around, very portable. And the really cool innovation is I believe that these two, they're both Hagelin type machines. There's actually a mode where they're compatible. So if I have this machine, I could send to this machine in one setting. So just like MS-DOS Windows had to be compatible with MS-DOS, the CD57 had to be compatible with the M209. And if you look inside of it, mechanically it's quite different than the way the M209 looks, but you have similarly all these letter wheels, and there are tiny little tabs on there, and there's a little tool in here for you to make those settings. And you can see here it's got a similar wheel. Every time you turn the crank, it rotates the code wheel a certain number of spaces away from the original letter. These are all Swiss. And then I have 2 more machines here. And I have 5 minutes, so okay. So this machine, I've actually never operated this machine. I'm actually blanking out on its name right now. I think I might have it. There it is, the CX52. Thank you. So if you study cryptography, there is one provably, absolutely secure system for sending messages that cannot ever be broken, and that's called a random tape or one-time pad system. And In a random tape or one-time pad system, you basically have a code for every letter of your message that you throw away after you send that one letter, and you never ever use it again. And so you have to have a method of generating a truly random sequence of keys or letters, and B, a way of distributing them securely to the people to whom you wish to communicate with in sufficient length that they will last for as many messages as you need to send them. So it's quite cumbersome as a system because you have to distribute these tapes. But it's totally secure. So
as long as you have the discipline to only use the tapes once.
Yes, you have to burn them, or you presumably need to destroy them as soon as they're used. Yeah. And if you reuse them, or like, let's just use last month's keys. Yeah, that's a problem. And I'm sure that stuff happens, just human nature. So I believe this is also, without the tape, it's compatible, I think, with these other Hagelin machines. But with the tape, it adds you can have a totally random sequence applied to your code. And the last one is just one. Okay, as a collector of these machines, I got into this habit, and it kind of consumed me for a while. I first bought the Enigma machine, and then this, and then this, and the Enigma was actually interesting because I was just on an internet mailing list for people interested in Bletchley Park, and someone mailed the mailing list one day and said, "I've got an Enigma, and does anybody know how much they're worth? Because I'm interested in selling it." And I sent him mail back saying, "I have no idea how much it's worth, but if we can find out a fair market value, I would love to buy it from you." So we did some research. We found some history of some recent auctions, and I agreed to fly to Washington, D.C., where he was living, and he told me he's a Russian professor, and he said a friend of his had given him this machine. A colleague of his had given this machine when they worked together in Germany. So he had it was a very favorite prized possession of his, but he needed some money for, I think, startup business he wanted to try to do, and so he was willing to part with his machine. So that one was just luck that I found that machine. Then eBay came along. And then once you start bidding in eBay for machines like this, people kind of know they start to remember your name, and so then I started getting unsolicited mail from people in Germany and Switzerland saying, "Oh, if you like that machine, you should see this machine I have." And so, but I had someone from Switzerland send me basically this machine, this, and the CD57, and a couple others I have still at home. He sent me this catalog. It was just like a candy store of machines that he had collected. I think he lived near the Crypto AG company, which made all these machines, or he was associated with them. So I just said, "Oh, I'll take one of that, and one of that, and one of that," and they were all really fascinating objects to have. So I bought them all. So I actually still don't even know exactly how to use some of them, but this is yet another kind of really early crypto system where you have these bars that slide and then a window that reveals letters, and I actually don't know how it works, but it looked pretty cool. So I said, "I'll take one of those too." With that, I think I'm done, and take any questions that you guys have. So Okay, one here in the room.
The question is, do you know of any systems that were used in the Soviet Union at the time, or during the war? Or
the Soviet systems, they have some teletype systems. There are, I have been offered for sale some of those things, and they've been on eBay, and I forget the names right now, but kind of maxed out my budget for collecting for a while after gorging myself on this stuff. Yeah.
What is the market price of Enigma?
I paid $18,000 for it, and I think it's well over $20,000 today for this. This is also, there are different types of Enigma. This one is called a service Enigma, so it has 3 rotors. The reflecting rotor doesn't move and is not interchangeable. There is a naval Enigma, which is called the M4 Enigma, which is much more valuable. It's probably more like a $40,000 machine. I have one of those as well, but I don't travel with it. And it has a fourth wheel here, which doesn't rotate in the sense of the notch. It has no notch, but you can set it at any of 26 different positions, including, it's called the beta rotor, and that rotor, again, has a compatibility mode, so if you set it in the A position, it acts just like the old 3-rotor Enigma, so it's compatible, but then you can shift it around to 25 different positions. And they use that on the military, the U-boats, and in the war in the Atlantic. That was the machine that was used for that. It's really the most famous version of the Enigma, and most rare. I also have another device for the Enigma called an Uhr, or clock, and it was used to. It's a weird adaptation on here. You plug it into all the plugs in the plug board, and it's like a crazy kind of. It's a way of changing your plug board settings every hour very conveniently. So you just kind of turn this little wheel, and they just have internally wired a whole new set of plug board settings. And so it's for applications where you need to change keys very rapidly and want to do it frequently, and so you can plug in an Uhr into this and change it. So it's weird how things evolve, and you get layers of complexity on top of otherwise simple systems to try to improve them. Yeah, pretty soon you have Vista in 5 years. Pardon me?
There was this kind of printer you put on top of it, right?
I'm not sure of an Enigma printer. Maybe, I don't know.
That's something on Wikipedia.
I have another device which was like I have one version of an Enigma. I think it was a commercial Enigma that has like a remote console, a remote set of lights. So I assume that was used so the person who's typing the code is not the person who sees the message, and someone else can see it across.
In this Swiss machine, there's also a second set of lights in the box.
Oh, those are spare lights. Spares. The Enigma also has a place to put spare lights in here. The first thing I did when I got the Enigma was to buy spares for all the original light bulbs, and happened to find one that fit pretty well, and so I didn't want to burn out the authentic original lights.
So Mike does have a plan. Any Berkeley questions? San Diego.
Thank you. Yeah, I got a question.
San Diego.
Yes.
Yeah.
So, I guess the security is called Ultra, right? It was supposed to be above the top secret security clearance they had to work on these. The people that. But what I was curious about, they had a 50-year classification on this. But then in '74 they declassed it. I was just wondering why it became so quick to say, okay, this is supposed to be the super high secure thing, but and then apparently someone, I can't remember who, but someone said, oh, we don't want to tell the Germans that we broke their code. Never tell them that, because then they'll say that we beat them unfairly, something like that.
Well, I don't know about fair or unfair.
But do you know anything about that? Why it just became so quickly declassed?
Well, I think probably because they realized it didn't really have much more value to the government at that point. Once these machines became out of circulation, the fact that those were decoded by Britain was, it had kind of leaked out. I think there were certain books written about telling the story that there were some decoding efforts, and even before the official acknowledgement of it, and but it's, I think it just basically didn't have any value anymore. Britain is pretty hard-nosed about maintaining security for a long time. It's kind of surprising that they had such a long classification of it, I think. Just, it's pretty obvious that everyone's trying to read everyone else's mail, even though gentlemen are not supposed to do so. So,
San Diego.
No more.
Nope.
Okay.
Berkeley has a question.
All right.
Winston Churchill asked for the destruction, or had the destruction of the Colossus. What's the story behind what happened to it? And I saw a part. There's one at the Computer History Museum. But why was it totally destroyed?
Well, they destroyed most of Bletchley Park and destroyed most of those records. And after the war, they again wanted to maintain as much secrecy as possible. A lot went into trying to make sure that the Germans didn't even suspect that their codes were broken during the war, and I'm sure they want to maintain that as long as possible. I'm not specifically. I don't have specific knowledge about the Colossus. I do know that Bletchley Park has rebuilt an entire replica of the Colossus machine, and I believe it's functional. They have a functional replica. I've not visited myself, but I'd love to go there someday. So there is now a museum there, and part of the original Bletchley Park site is starting to be developed, and there was an effort to try to make it a national monument so that the original, I think, Hut 6, and they have different names of huts where different parts of the cryptanalytic effort were carried out. So they're trying to preserve as much as they can. There's original kind of a castle or a manor house, and then there were these different huts around where people would work. It's like an estate kind of thing.
And just for
let's let San Diego have the question. There was one in San Diego, was there?
Yeah, question?
Yeah.
So, how might the Colossus have influenced subsequent computer architectures if it hadn't been covered up?
Well, I think that's a really good question. I mean, obviously, secrecy does delay innovation if people can't copy what you're doing. But, like most innovations in the world, it's pretty rare to invent something totally out of whole cloth where the idea isn't imminently attainable by somebody else who's concentratedly thinking about it. So
I could be totally wrong, but my impression was Colossus was not a general purpose machine.
I'm not 100% sure about it, but I don't know.
I have a feeling it was sort of an idiot savant cracking code.
Yeah, I think Colossus had some components of stored programming in it, but I'm not 100% sure.
It was programmable with plugs.
Maybe with
and
plugs.
Somebody was able to program it to do some generic stuff, but it was mostly.
But I think it probably delayed some innovation, but I don't think you can stop an inevitable idea like building a computer once you have electronic circuits and other kind of expertise like that.
Okay, is there a last question anywhere? Perfect. So let me, before we thank Mike one last time, remind everybody to please turn in the course evaluations. If you'd like the class, turn in 2 or 3. Margie in the back here will collect the ones in this room. I want to thank the tech staff, Rod and Fred here in the folks at Berkeley and San Diego for making this happen. And Mike, thank you.